Welcome back to AI Paper Podcasts. Today, we're really digging into a problem that honestly plagues pretty much every ML engineer trying to get computer vision working in the real world: data curation.
Oh yeah, this is a massive bottleneck. We've got these amazing models, but getting the right data, cleaned and labeled, especially for specific domains, that's where things grind to a halt.
Exactly. The tools have felt kind of fragmented, very manual for a long time. But this paper we're looking at today, Labeling Copilot, a deep research agent for automated data curation in computer vision, suggests a really different approach. It's about automating the whole research cycle.
It really is a shift. If you're dealing with, say, industrial inspection, tricky robotics, or specialized medical scans, you know the pain. You've got these huge unlabeled data lakes. And you need quality, you need diversity, but you're also fighting cost. Labeling Copilot is framed as the first deep research agent designed specifically for this.
A deep research agent.
Yeah.
Okay, so its job is basically to juggle all those trade-offs, quality, diversity, costs, that normally take teams weeks or months.
Precisely. It's trying to automate that complex decision-making process.
Okay, cool. So for our short-form edit folks, give us the quick version. What are the three key things this agent actually does?
Right. So it ditches the old, rigid data pipelines. Instead, you have this dynamic agent that uses three main tools. First up is Calibrated Discovery. Think active learning, but rebuilt for serious scale using FOGES. They're seeing up to 40x speedups on 10 million sample data sets.
40 times. Okay, that's significant. What's number two?
Second is Controllable Synthesis. It's pretty neat. It uses language prompts to get diffusion models to generate very specific synthetic data. So if you need images of really rare events like weird object poses or specific weather conditions that are hard to find, it can create them. Fills those critical gaps.
So targeting the long tail or safety critical stuff. And the third piece, how does it handle the actual labeling, especially when models disagree?
That's tool 3, Consensus Annotation. It basically takes a bunch of different foundation models, DTIC, grounding DNO, that kind of thing, and fuses their outputs. It uses this novel voting mechanism and Soft NMS to handle disagreements and overlaps.
And does it work? What's the punchy result?
Well, the consensus annotation part hit a mean average precision, an MAP, of 37.1% on COCO, which is pretty dense. And maybe more impressively, on open images, which has crazy class imbalance, it actually discovered 903 new bounding box categories. So it's not just labeling, it's finding new stuff.
Wow, 903 new categories. That really does change the game for data set building. Okay, let's dive deeper. How does this agentic workflow actually tackle what you called the demons of data curation: scale, rarity, and ambiguity?
Yeah, those are the big three hurdles, right? They're all tangled together. First is scale. You've got these enormous data repositories, LAION, DataComp, millions, maybe billions of images. How do you filter out the junk or just the irrelevant stuff efficiently?
Right, you can't afford to label everything, especially the noise. Then the second demon, rarity. How do you make models robust to things they barely ever see in the training data? Like a specific type of machine failure or weird lighting or that safety example of a worker under a suspended load. Stuff that's critical but rare.
Exactly. Data you probably won't find easily, if at all, in your initial scrape. And the third demon is ambiguity. Okay, manual labeling is slow, it's expensive, so you try automated methods, foundation models, but they often give you conflicting answers, noisy labels. How do you resolve that?
And this is where the deep research agent idea comes in. It's not just a script, it's this orchestrator, probably a large multimodal model, running that continuous loop: discover, hasticize, annotate, and filter, making decisions based on quality signals.
That's the key difference. It's dynamic, not linear. It decides what tool to use when, based on what it's seeing in the data.
Okay, let me break down the tools. Tool 1, Calibrated Discovery, tackling scale. You mentioned active learning falls apart at scale.
Yeah, traditional active learning, the canonical stuff, it often needs to calculate distances between all points or run the model on every single unlabeled sample to find the most informative ones.
Which is just impossible if you have millions or tens of millions of images. The compute cost is astronomical.
Totally unfeasible.
Yeah.
So the agent needed a way to make AL efficient without needing to scan everything. The core technical idea was rebuilding AL using the H8S library. AAS is all about approximate nearest neighbor search.
Right. AAS is super popular for vector search. How does it specifically help with the scale and memory issues here?
It uses a couple of really clever techniques.
Yeah.
For search speed, it uses IVF, inverted file systems. Instead of checking every single vector, it partitions the whole vector space into cells and only searches within a few relevant cells. That drastically cuts down search time from like linear ON to something much smaller.
Okay, so faster searching. What about memory? High-dimensional vectors take up a lot of space.
That's where product quantization PQ comes in. PQ is a compression technique. It takes these big high-dimensional vectors and represents them using way fewer bytes, sometimes as little as 8 or 16 bytes per vector instead of hundreds. That's what makes it possible to keep huge indexes in RAM.
Got it. Faster search, smaller memory footprint. But wait, you said approximate nearest neighbors. Doesn't that mean FAICS might miss the best samples for active learning? Are we losing accuracy for speed?
That's the crucial trade-off they tackled by reformulating the AL algorithms themselves. For the selection part, they used an approximate version of k-center greedy. Instead of finding distances to all unlabeled points, which is the expensive part, it operates on a small, fixed-size pool of candidates. Let's call it NC.
So the runtime doesn't depend on the total number of unlabeled images anymore, just this candidate pool size.
Exactly. It decouples the complexity from the size of the entire data lake.
Yeah.
And the results showed this approximate version was just as good in terms of sample efficiency. They got 0.90 AUC, matching more complex methods, but it was 40 times faster computationally.
40 times faster with basically the same quality? That's huge. What about calculating the uncertainty scores for those samples? Doesn't that still require running the model a lot?
They optimize that too, using what they call localized acquisition. Instead of running the model over the whole data set, or even the whole candidate pool, it uses the ANN index, again, to find just a small local neighborhood, new, around a potential sample, and only calculates uncertainty within that neighborhood. Much cheaper.
Okay, so Calibrated Discovery finds a diverse, informative batch efficiently. But how does it make sure this batch isn't full of, I don't know, cat pictures that somehow got mixed into my data set of industrial parts? How does it filter out irrelevant stuff before labeling?
Good question. That's the OD filtering step, acting like a semantic guardrail. After finding potential samples, it uses a technique adapted from typicality estimation. Basically, it builds a statistical model, like a Gaussian mixture model, GMM, of what your in-distribution data looks like.
Like defining the normal pattern.
Right. And then for each retrieved sample, it checks how well it fits that normal model. If the sample is too much of an outlier, statistically speaking, if its probability under the GMM is below some threshold, it gets tossed out.
So it saves the labeling budget for things that actually fit the target domain. Smart. Okay, Calibrated Discovery handles scale. But what if the data you really need, maybe for safety reasons or because it's super rare, just isn't in your data lake to begin with?
That's precisely when the agent switches gears and calls on Tool 2, Controllable Synthesis. This is where it tackles the rarity demon.
So Discovery says, hey, I can't find enough examples of workers near operating machinery at night.
Something like that. Discovery signals a lack of diversity or specific rare cases. Then the synthesis tool kicks in. And this isn't just random image generation. The agent uses multimodal LLMs, like GPT-4o, to generate very specific, fine-grained editing instructions.
Instructions for what? Like text-to-image prompts?
Exactly. Or image editing prompts for models like Instruct Pixapigs or Stable Diffusion. So you're not just asking for a car. You're asking, like you said, for a car at night in the rain from a high angle. Or that critical safety example. A worker standing directly under a suspended load.
Things you might never capture safely or ethically in the real world.
Precisely. It allows generating data for scenarios that are vital for robustness or safety, but practically impossible to photograph. But crucially, it's not just generate and dump. The agent includes a rigorous validation step before adding synthetic data.
How does it validate? What's it looking for?
It uses a whole suite of metrics focused on 4 main things. Fidelity and diversity. Does it look real? Is it varied? They use things like FID, KICKAD, precision recall, and DynaV2 space. Rarity, is it actually hitting the rare case we asked for? And importantly, memorization, especially if using fine-tuned generators, is just regurgitating training data. They check that with things like auth-PCT.
Okay, so the agent diagnoses the gap, uses generation to fill it strategically, and then validates the quality before it even touches the main data set. That feels like a much smarter loop.
It's definitely more sophisticated than just bulk synthesis. And that leads us to the final tool, Tool 3, Consensus Annotation, which tackles that third demon, ambiguity. We have all this data now, real and synthetic, but how do we get reliable labels without expensive humans, especially when automated models often disagree?
Right. If you run DDIC and grounding Dino on the same image, they might find slightly different boxes or even different objects.
Exactly. So the agent uses an ensemble approach. It orchestrates a heterogeneous group of these foundation models, DDIC, grounding Dino, OWL, VIT, potentially others. The goal is to get models with different strengths and weaknesses, ideally uncorrelated error modes.
The classic ensemble benefit. How does it manage running all these potentially heavy models at scale?
The whole annotation process is designed as a massively parallel pipeline, meant for high-performance computing, HPC clusters. A really key design choice here is standardization. The output from each individual model, the weak labels, is saved as a standard Pascal VOC XML file.
Ah, so generating the proposals is separate from fusing them.
Exactly. It decouples those stages. That makes the whole thing more scalable, more fault-tolerant. If one model run fails, it doesn't break the entire pipeline. You can just rerun it.
Makes sense. Okay, let's get to the fusion magic. How does it combine all those different XML files with potentially conflicting bounding boxes?
It uses a mechanism called support-based matching. Instead of just comparing pairs of boxes like traditional non-maximal suppression, NMS, it looks at reconciling predictions from multiple models at once. It clusters proposals based on spatial overlap, I/O.
Okay, it groups boxes that seem to point to the same thing. Then what?
Then comes the core innovation. The consensus score, let's call it S. This score isn't just averaging the confidence scores from the individual models. It's a measure of how many different models in the ensemble agree on that cluster. It's calculated as the proportion of unique models that have at least one prediction in that cluster.
I see. So a box cluster supported by, say, 3 different detectors gets a much higher consensus score than a cluster supported by only one, even if that one model is very confident. It rewards inter-model agreement.
Precisely. It inherently upweights detections that multiple diverse experts agree on, which are likely to be more robust and accurate.
And after calculating this consensus score, there might still be overlaps.
Right. So the final step is a configurable NMS module to resolve any remaining spatial overlaps between the consensus clusters. But critically, it uses that reliable consensus score S for sorting the boxes before suppression.
And did they find a particular type of NMS worked best?
Yes, they tested different variants, and Soft NMS consistently gave the best results, particularly the highest MAP and recall, especially on dense data sets like Kokio.
Why Soft NMS? What's the advantage there?
Because in crowded scenes, imagine tools scattered on a workbench. Traditional NMS can be too aggressive. If 2 valid tools overlap slightly, standard NMS might just delete the one with the lower score. Soft NMS instead just reduces the score of the overlapping lower scoring box based on the overlap amount, rather than eliminating it entirely. It helps preserve valid detections in clutter.
That makes a lot of sense for real-world messiness. Okay, let's talk quantitative proof. We heard the 40x speedup for discovery. What about the final annotation quality from this consensus approach?
Well, first, the system is designed to be prolific, to aim for high recall initially. On Coco, for instance, the ensemble generated about 14.2 candidate proposals per image, which is almost double the actual number of ground truth objects.
So it casts a wide net first.
Right. Then the consensus mechanism, especially the Soft NMS, distills that down effectively. They achieved an overall MAP of 0.371 on Coco test dev, and MAP at 0.75 was even higher at 0.401, showing it works well even for tightly localized boxes in dense scenes.
And that open images result really underscores the discovery aspect, doesn't it?
Absolutely. Open images is kind of a proxy for messy web-scale data with huge class imbalance, lots of rare stuff. The fact that the agent, using this whole discovery synthesis annotation loop, managed to find and label 9 out of 3 new bounding box categories, that's huge. It increased the total number of categories it could handle to over 1,500. It proves the whole system isn't just for refining existing datasets, but for genuine, large-scale discovery.
Okay, this feels like more than just a collection of tools. The paper talks a lot about the design philosophy, the architecture. What's the bigger idea here?
This is maybe the most interesting part for people building AI systems. The core philosophy is treating the main operations, discovery, synthesis, annotation, as timeless primitives. The agent orchestrates these fundamental building blocks.
Timeless primitives, meaning the what discovery, synthesis, annotation is more fundamental than the how the specific model used today.
Exactly. This leads to what they emphasize as a critical architectural principle. The agent's core workflow, its strategy and decision-making logic, is deliberately kept separate from the specific implementations of the tools. The intelligence is in the orchestration, not just the individual models.
Which makes the whole system hot-swappable, right? Like tomorrow, if a much better open vocabulary detector comes out that blows grounding Dino away,
you just swap it in. As long as the new model conforms to that standardized interface, like outputting Pascal VOC XML, the agent doesn't need to change its core reasoning loop. It just has a better tool to call upon.
That seems incredibly powerful for keeping up with the pace of model development.
It is. They call this decoupled intelligence. The strategic thinking of the agent, when to synthesize, how much data to discover, which models to query for annotation, is separate from the execution engines, the tools themselves. You can improve the agent's strategy and improve the tools independently. It makes the system far more robust, extensible, and, frankly, future-proof.
So wrapping this up, what's the big takeaway? Labeling Copilot feels like a significant step beyond just better models. It's about automating the process of data-centric AI.
I think that's right. It's a shift from these fragmented, often manual curation steps towards a more integrated, intelligent, automated research workflow, truly built for industrial scale and complexity.
And that idea of decoupled intelligence, separating the strategy from the tools, that seems like it could apply much more broadly.
Definitely. The agent tackles the data curation bottleneck now. But imagine if that orchestrator agent's strategic reasoning capabilities keep improving independently of the tools it uses. It really makes you wonder, is the next big leap in AI infrastructure going to come not just from bigger foundation models, but from smarter agents coordinating swarms of specialized models? It's a provocation, maybe, for you listening. Think about your own complex workflows. Could they be broken down into these kinds of timeless primitives coordinated by a higher level intelligence? Where could that take you?